Hi. In this set of lectures, we're talking about economic growth. And what we want to do is we want to understand why is it that some countries are rich and some countries are poor. So to get our bearings on how growth works, we've got to start with a much simpler model. Because our economic growth models are going to have a lot going on. They're going to have labor, they're going to have physical capital, they're going to have depreciation rates and saving rates and all sorts of stuff. So to just sort of get us to understand the basics of growth, we're going to start out with a much simpler case. And we're going to start by talking about just compounding. So you put money in the bank, we talk about the rate at which that grows. And from then, we're going to talk about then countries growing, talking about GDP growing, and we're going to see why different growth rates are so important. Because we're going to see that, again, growth is sort of exponential. So we're going to talk about just a very simple sort of exponential growth rate where we just keep putting money in the bank. From that, we're going to learn a really cool trick called the rule of 72. The rule of 72 will tell us how quickly our money will double or how quickly GDP will double. So therefore, if you think about what's the difference between an 8% growth rate and a 4% growth rate, you might think it's twice as much. We'll actually see, according to the rule of 72, that it's even more than that. That doubling the growth rate has really significant effects. Okay, so let's get started. So let's start with just sort of like, basic accounting 101. You put some money in the bank. So let's suppose you got X dollars and you put it in the bank at R% interest. How much do you get? Well, let's suppose you got $100 and you put it in the bank, and let's suppose you get 5% interest. Well, what you're going to get at the end of the next year is $105, right? Because the general formula for this thing is you just take X times 1 plus the interest rate, right? So that's the general formula. So if I put $100 in the bank at 5%, I'll get 105 back. Now if I put that 105 back in the bank, I'll get 105 times 1 plus 0.05, and that's going to be 105 plus 5.25, which is 110.25. So at the end of 2 years, I'll have 110.25. Now, if I kept this money in the bank for 10 years, I'd just have 100 times 1 plus 0.05 raised to the 10th power, right? Because I just keep multiplying this by 1.05 times 1.05 times 1.05, and that's what I get. So that's, if you want to think about if I buy a certificate of deposit for some money, the bank say, okay, I'm going to put this $1,000 in for 6 years at 5%. They'll tell you, okay, well, then you're going to get $1,000 times 1.05 raised to the 6th power. That's how much you get back at the end of the 6 years. We want to do that same thing, same very, very simple thing with GDP. Now with GDP, what we're going to do, instead of having X be the amount of money we put in the bank, that's going to be per capita GDP. If there's a GDP right now of G and we have R% growth, then next year we'll get 1 plus R. And in 10 years, we'll have 1 plus R raised to the 10th power. Now, why does that matter so much? Why do we care so much about this R? Why do politicians always talk about it? Why do bankers always talk about it? Why do we care so much about growth rates? Well, to see why, let's look at two cases. Let's look at a sort of low growth case, a country that has a 2% growth rate, and a high growth case, a country that has a 6% growth rate. Let's start them out both in year 0 with everybody making $1,000. So per capita income's $1,000. Well, what happens after the first year? For the first year, the first country goes up by 20%, so it's 1,020. The other country's at 1,060. Now you could say, big deal, $40 more per person. That's not a huge difference. Well, let's go ahead 10 years. In 10 years, if I use that formula, the people in the first country are making $1,200 apiece. People in the second country are making $1,800 apiece. So now they're 50% better off. And if I go ahead 35 years, right, so really maybe one generation, maybe generation and a half, the first country's now doubled, right, so they're at 2,000. The second country's at 7,600. They've gone up 3.8 times. So now they're almost, or 7.6 times, I'm sorry, so they're almost 4 times better off. Let's suppose I go ahead 100 years, move ahead a century. One country plugs along at 2% growth. The other country plugs along at 6% growth, right? The first country's now making $7,000 per person. The second country, right, people are making $339,000 per person, right? So that's like 45 times as much. So in a 100-year period, this 2% versus 6% difference just becomes enormous. And that's because this growth is exponential, right? Because it's 1 plus R raised to the power T. And so if R is bigger, you get a huge increase. So here's the rule of 72. And this explains sort of why what was going on in that graph. The rule of 72 says, divide the growth rate into 72, and the answer you get will give you the number of years it takes to double, right? So let's suppose our growth rate is 2%, right? If our growth rate is 2%, I take 72, divide it by 2, and I get 36. That means it'll take about 36 years to double. Let's go back to our graph. If you go back to our graph, you see it took 35 years to double. So pretty close, right? What if I had 6%? Well, 72 divided by 12, divided by 6 means that it's going to be 12 years to double. So what that means is, in this first period, the 2%, it's going to take me 36 years to double. At 6%, it only takes me 12 years to double, which means that this country will double 3 times, which is 2 times 2 times 2, which is 8. So its GDP will be 8 times its original GDP in the time it took the first country to double. And if we go back and look at our data, sure enough, after 35 years, it's effectively 8 times as big. So you see the rule of 72 isn't exactly right. Like, it took only 35 years to double, and this isn't quite at 8,000, but it's really accurate. So for low interest rates, it tends to, overestimate the number of years, and for high interest rates, it tends to overestimate the number of years. But if it at 8% or 9%, it works just about perfectly. So the rule of 72, right, again, which is really cool, so it's just, look, take your growth rate, divide it into 72, that tells you how long it's going to take to double. So the move from 2% to 6% isn't just a 4% increase in the growth rate, right? It's a dividing by 3 of the time to double. So it means that every 12 years, your country's going to double its well-being, its GDP. Whereas in the first case, at 2%, it's going to take 36 years. That's why people focus so much on growth rates, and that's why we want to look at models that explain where growth comes from. Let's go back and look at the United States. Remember, we're hanging out about 3-4%. Well, you can think, what's the difference between 3-4%? Well, 4% is 72 divided by 4, which means every 18 years will double. And 3% is 72 divided by 3, which means every 24 years will double. Well, what would you rather do? Double every 18 years or double every 24 years? Clearly, you'd rather double every 18 years. So that's why we care a lot about boosting that growth rate, even from something like 3% to 4%, because it means we're going to increase our well-being much, much faster. Okay, exhale. There's a lot going on here, right? We've talked about this sort of, simple interest rate thing where we've got x, right, times 1 plus r raised to the tth power. Well, this is sort of a sheet here because what I've done is I've just assumed, for the interest of simplification, that the growth is happening just once a year. So it's like once a year we do growth rates. When I was a kid, there was a commercial on television for a bank, and they talked about how some banks only gave interest once a year. And it said, this new bank, we give interest every second of the day. So what we do is, instead of saying, okay, we're going to give you at the end of 1 year x times 1 plus r, we're going to give you interest, let's just say, suppose first we're going to give you interest every day. So we're going to give you 1 plus r over 365. So we're going to reduce the rate, divide it by 365. We're going to give that to you 365 times. So we're going to compute your interest daily. And then they said, we'll even do better than that. We're going to do it, we could even do it hourly. So we'll do it over, we're going to divide the interest rate times the number of hours in the day, and then we'll compute this interest every hour. And then we could even do it every second, and so on and so on and so on. And they showed this guy a calculator, just plugging away, right, computing these interest rates. And I thought, how are they doing that? Well, the way they did it is they just used math. It turns out if you have this formula, and this should be an infinity here, if you have the number of periods go to infinity, right, so if you're doing it infinitely fast, then what happens is this formula, this 1 plus the interest rate over n raised to the power nt, just becomes e to the rt. And remember, e was that number, Euler's constant, which is 2.71828. So why do we do this? Why do we do all this math? The reason we're doing all this math is basically you can think of the growth rate, instead of thinking of this formula, x times 1 plus r to the t, you can do something simpler. You can just use e to the rt, where e is this Euler's constant, this 2.71828. So what you can do is, if you think about growth as just sort of occurring continuously, in this nice simple formula will give you sort of the rate at which things are going to grow. And that's why it's called exponential growth, because the rate at which you grow is exponential in this function, in this number e. So it's e raised to the exponent rt. So why is that so important? The reason it's so important, let's go back. Remember we talked about linear functions in the previous set of lectures, right? So remember, a linear function looks like this. So that would mean that growth would sort of go 10, right, 11, 12, 13, 14, and so on, right? Exponential growth goes like this. It zooms up even faster than something like x squared. So what that means is if you grow at a 10% rate, right? You're not just going to go 10, 11, 12, 13, 14, 15, 16, right? In fact, if you grow at a 10% rate in 7 years, right? Remember the rule of 72, 72 divided by 10 is equal to 7. In 7 years, what you're going to do is you're going to double. So you'd be twice as well off as you were before. What have we learned? We've learned that if we have a growth rate of, say, let's say 3%, 4%, 5%, right, that can lead to significantly better, higher GDP down the road than if the growth rate's just a little bit smaller. And the reason why is because you've got this exponential growth. The outcome is not going to be sort of linear in these growth rates, right, but it's going to be exponential over time. So what you'd like to do is sustain a higher growth rate. So what we want to do next is construct some models of growth where we can see how does economic growth depend on things like savings, depreciation, and technology. Okay, thank you.